How those warm-ups going? Which one are you on? First one? Jeez, Louise. 4? Oh. Should I make you do the second one in a different way, or no? I'll let you.
Yes.
All right. Can you use? Would you want to use direct comparison test on the first one? No, the inequality work would be terrible. So limit comparison makes sense. Does the limit? Would the direct comparison even work for 11?
Yes.
It would be a case that would work, but if you already started it, that's fine. I forgot. Okay, and the last one. What'd you get for the last one? Or are you not done yet?
Not
Done. Yeah. All right. What did you get for an answer for 14? 0? Not 0. Cat? Indeterminate.
Yes.
Oh, yes. Okay. As A goes to 2, does this go big or small? Small. 1 divided by negative tiny is? Negative big. Plus 1/8. Minus 1/8. Big minus 2 is little squared. 1 over little positive little squared is? Big positive. Negative infinity plus infinity, or infinity minus infinity, is indeterminate, and there is no more to do. They're not the same limit. They are not log rules. I can't put them together. You're just stuck. There's no way. You with me? All right. It sounds like we need more work on those bad boys. Here we go. Movie time. Just a little bit of movie real quick.
When the capsule moves from an elliptical orbit to a parabolic, there's no mathematical formula for that. We can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's
Euler's method.
yes,
That's ancient.
but it works. It works numerically.
That's it.
Let's type it up.
That's a good one. That's a good movie. You should watch that movie if you ever haven't seen it. It's really good. Okay, so Euler's method. That's today. Euler's method. So this is Euler was it's Euler, by the way, not Euler. It'll make me crazy if you say Euler. It's Euler. Okay, he's a Swiss mathematician in the generation after Newton and Leibniz. So he's following in the footsteps, and he's taking calculus and these new methods. It's a good time to be a great mathematician because there's all these different ways to apply the calculus that haven't been taught. All right, so in order to get there, first, would you remind yourself how we use differentials? Would you estimate the square root of 27 using differentials? And we'll go over it in a minute to make sure you have the big ideas down correctly. Quality work is what's important, that's what's good. Okay. Here we go. Would you agree that the square of 27 is the square of 25 plus some true change? Yes? And that can be estimated by the square root of 25 plus some differential change. And we know that the big idea of differentials is that if you take that big derivative fact and separate the differentials, that the estimated change in y is the rate of change times some change in x, okay? Right? All of that's what you're looking at. Now that is the foundation for Euler's method. We'll come to it in a second here. What is the derivative? And at what value? 25 or 5? 25. And what's dx? 2. That 2, does it come from 27 minus 25 or 25 minus 27? 27 minus 25. Generally, I use common sense to do that, but sometimes it's not going to be a common sensey problem. So it's kind of the end minus the start approach. So did you get something like 5 and was it a fifth? Yes? Okay, cool. Now, when you estimate using differentials, then we say some new y is an old y, or can be estimated by a new y plus the rate of change at a point times an amount of change in x. Yay? Cool. All right. Dx or delta x, in this case, these delta x and dx are the same because either way it's how much you choose to go over by, so don't get hung up on that. Now, second idea, this is off the edge a little bit. I need to make that a little smaller. Sorry, just a second. Okay. All right. Now, towards the idea. It's very much a differential equation idea. Would you draw me a slope field for dy dx equals 2x? For, yes, all those points. It doesn't have to be perfect to get the idea. Precision here is nice, but not desirable, but not perfect. Okay, something like that. They should be getting steeper as you go right. Yay? And they should be the same going up and down in any one x. All right. Would you draw the particular solution through 0, 0? Now let's actually, you just follow it. Just give me a rough sketch through 0, 0. So put a point at 0, 0 and tell me where would the slopes take you. I'm going to say something like that. Do you agree? Okay, it start out going pretty flat, but as soon as you go off, you're going a little more steep. Would you do part C? Would you find the actual solution by separation of variables? I think you'll agree y equals x squared, yes? All right, cool. We're getting there, just a little bit at a time. So say you're interested in f at 4. What is f at 4? 16, yeah? Given that you know the function is y equals x squared, f at 4 would have to be 16, right? Okay, now, here we go. If you use your slope field, particular solution through 0 to estimate f at 4, in other words, you're going to put your point here at 0, and you're going to follow that one slope to what you think y would be at 4. Well, what does that slope say? That slope at 0 says that as you change x, y changes nothing. And so it seems like that would tell you that f at 4 should be about 0. Okay? Now, obviously that's a terrible estimate. Why is that a terrible estimate? We know it's 16. What if you didn't know it was 16? Why could you still know that's not a very good estimate? Why is that such a bad estimate of where the curve truly is at 4? Far away. Okay, what else? Starts changing. What starts changing? Okay, that's what I was looking for. All right. The slopes change after leaving 0. You need to use new slopes. Now that was Euler's idea. We do this, you have been doing this since your first few weeks of Calc 2, or Calc 1, sorry. We often use a tangent line to say, you know what, I can make a tangent line at 1 and estimate f at 2, and these are pretty close, yeah? Tangent lines all the time. Now, Euler's like tangent line on steroids here. It goes something like this. What if, keeping this idea of saying, well, the slopes change right away, we recalculated slope. So if we started by saying, all right, we'll start with 0, 0, and we're going to let our first x estimate be only, now, actually, when I say 2 steps, we're going to talk a delta x of 2. I'm going to try to go from 0 to 4 in 2 steps, so I'm going to break it into 2 separate chunks. You with me? Okay, x1, then the first x was 0. The second x will be what do we get when we get to an x of 2, yeah? And our y, our first y estimate would be our, now here's where we use that differential word. When we do differentials, we say we take the old y plus the rate of change at the previous point, 0, 0, times dx or delta x, and it's pretty common to use delta x, but I would be okay if you used dx too. All right, you with me? That's the differential idea. Now, in this case, what was our old y? 0. And what is the rate of change at that previous point? 0. And how much are we going to change x by? 2. And so what do we say our new y is? 0. That is to say that if we take the rate of change at 0 and go over 2 units, I would still be, when I got to an x of 2, y would still be 0. You follow? But now, let's go and recalculate using a different slope now. Now, our second x that we're going to get to is now going 2 more units over, which would take me to an x of 4. You follow? The second y that we get after changing is our previous y. Now, our previous y is y1 plus the rate of change at our previous point. Now, that's going to be the rate of change not at 0, 0 anymore, but at 2, 0. And we're still going to go a delta x over as per the differential idea. You follow? Now, what was the previous y? 0. We left off with 0, but now we're going to recalculate and use a different slope. The slope at 2, 0 is, remember the derivative is 2x, right? So the slope at 2, 0 now is 4. It says, oh, when you get to that point, you should be going up 4 over 1 times the change in x of 2. So we would expect to go up 8 by the time. That would say, oh, if we make, instead of one tangent line that's terrible, we make 2 tangent lines, then we do a little better job of following the curve, which is here. Now, we're not perfectly on it, but at least it doesn't keep going in the wrong direction like we were going when we did one step. You follow me? All right, now we can do better. Just like Newton's method, we use repeated iterations. Same with Euler's method. If we did in 4 steps, if we went from 0, x equals 0, to x equals 4 in 4 steps, what's delta x? We're going to go by 1. All right, so our initial x is 0, our initial y is 0. Our first x is 1, and our first y, again, I expect formula, substitute, evaluate. So 3 little steps per iteration. Y initial plus dy dx at 0, 0 times the delta x this time of 1, right? But formula first. Cool? What's y initial? 0. What is the rate of change at 0, 0? 0 times the delta x of 1. Our first iteration takes us to 0. Now, in the picture, that would be, you're going to go over 1 unit horizontally, and y is still 0. But now we're going to recalculate our slope. x2, we're going to go from 1 to 2 now, so we're going to say what happens by the time we get to 2. y2 is y1 plus dy dx at the previous point. And what was the previous point? 1, 0 times the delta x formula. Check. Substitute. What's y1? 0. What's the slope at 1, 0? 2 times an x change of 1 tells me that as I go from an x of 1 to an x of 2, y goes up by 2. You see? All right. x3 will be 3. y3 is y2 plus dy dx at the previous point. The previous point was 2 times the delta x. Substitute. The previous y we left off at was 2. What's the rate of change now? 4 times the delta x of 1, which will take me to a new y of 6. 3, 6. And finally, our last x is 4. y4 is y3 plus the dy dx at the previous point, 3, 6 times the delta x. What is y3? 6. What's our new rate of change? 6. What's our amount of change in x? So our final y is 12. Now we're starting to follow the curve all that better. If you were to sketch the true curve in, it's 1, 4, 9, 16. We are doing a little better job of following. Whoa. All right. How can we get even better and better? Infinitely many steps. Taking a limit would be cool, but I don't think you do that. So here we go. Obviously, the more recalculations of slope or steps you use, the better the estimate. This is not a new idea. More precision from more subintervals or iterations also happens, and give me one thing that happens in it. What else do you do? More subintervals to get a better estimate. Rectangles or Riemann sums. Yes. What else? Trapezoids. True. How about Newton's method? Didn't we do repeated iterations of Newton's method to get a better estimate, etc.? Lots of times you do that. All right. This repeated estimation and step is Euler's method. Why do it at all? Why not just integrate? If we knew that, if we just got x squared and we put 4 in and get 16, why do all this stuff if I know it's going to be 16? You don't always, not everything can be integrated. So Euler's method is typically used for a non-integrable function. And despite the fact you can't integrate it, you can estimate the actual function value because you know how it changes. And that is pretty cool. All right, so big idea is this. Given a differential equation, dy dx or y prime, typically you would sometimes call this just f of xy. The derivative, a differential equation, can depend on both x and y. For example, the old circle. What's the differential equation for the unit circle? Negative 2x over negative 2 over 2y, so negative x over y. It's very common that derivatives depend on x and y. Anytime it's a non-function, you would need to know the x and the y. You down? So the derivative might depend on one or both. And this then is the big idea of Euler's method. A new y is the old y plus the rate of change times the change in x. This is an example or two and an AP example as well. Say you had dy dx is 2x minus y, which is a non-separable differential equation. That is to say, you cannot separate the variables in integrate. If I asked you to estimate y of 4 using an initial of 1, 0, and 2 steps, then this is what I suggest. First, find delta x. Delta x is the final x minus the starting x divided by the number of steps. What's delta x in this case? 1.5. You're going from 1 to 4. Remember, you got to look at the right values. You're going from an x of 1 to an x of 4 in 2 steps. And so that is 1.5. You follow? 4 3/2. Okay. Now, basically, you chart as you go. Each time you're going to find, say, at this point I'm at this x, and here's the y that goes with it. And the y is usually where the work is. X is just keeping track as you go sideways where you're at. So what's x initial? And what's y initial? 0. x1 then will be the initial x plus the delta x. So where's my first x? 2.5 or 2.5 or 5 halves, whatever you like. I expect each time you do Euler, formula, substitute, evaluate each time. So y1 is y initial plus dy dx at what point? 1, 0 times delta x. Formula. Check. Substitute. What is y initial? 0. dy dx at 1, 0 is something like 2 minus 0 or 2. And if you just put 2, I'd be fine with that. And delta x is 1.5. All right? So I started at 0, I went up 2 over 1 for 1.5 units, and that puts me at 3. Okay, cool. X2 then will be another delta x from where I left off. You were at 2.5, you went up 1.5, that puts you at 4, the ending destination, yeah. And y2 is y1 plus the rate of change at the previous point. What point will I find the derivative at? 2.53, and the delta x is still 1.5. I was curious to see if you ever use a different delta x. I could not find such an example. It seems like you always use equals subinterval. y1 is 3. This should be y1 here. I mislabeled that. That's y1. y1 is 3 plus the rate of change at 2.53 is, I agree, 2 times 1.5. So what is 2 times 1.5 plus 3? 6. Now, you'll notice that in all these they're equal because these represent Euler estimates. But when you go to express your answer, if you were to say y at 4, it is approximately 6 is your final answer. Remember, Euler is an approximation method. So in your final answer, you should make clear that, hey, I know this isn't the exact value, it's an approximation. Okay? Try one on your own. Get 13 for first iteration. Negative 455? Okay, so we would say f at 8 is approximately negative 455. Yeah? Okay, good deal. Let's finish. We probably won't get to homework questions, so we'll do it tomorrow, and tomorrow's a catch-up day anyway. Try one. So these are pretty big deal calcs too. It's most common that you see one multiple choice and it shows up in a part of a free response. So that it's, and not to mention it's just a big idea for DiffyQ. So it's a good skill. This is a good example of where it would show up in a free response. Try it out. you see about delta x here?
Negative one.
It is negative 1/2. It absolutely can be negative. You're going from x of 1 down to x equals 0. Delta x is negative 1/2. What did you get? Did you get an estimate yet? You got negative 5/4. Do you agree?
Yes.
Cool. Excellent. The rest are not new, but they're good Calc 1 practice, so it's worth doing. I want you to do them. And hopefully you would be looking at a 9 in such a question. What? Why? Did that go through? Did you just say why, but nothing else? Oh, no. No, you don't need the equation of y to do b. Otherwise, they would have had you do c before b, and therefore c would be b. B would be c. Let's say it's continuous. Uh-huh. Right. How'd you do on B? What are you thinking? What's your methodology? Yeah, how do you know it's continuous? That's the differentiable. The derivative exists. Do you agree that at x equal 1, the derivative exists? Okay, and therefore it must be differentiable at x equal 1. All right, so cool. Doesn't that imply then that the limit as x goes to 1 of f of x is the 0 they give you in the point? Yeah? Yay? Did you show good L'Hopital work? You didn't do this monkey business over here, did you? Because that'll lose you a point, guaranteed. That's a no-no. So yeah, L'Hopital. So you got 1/3? Yay. Then, now let's see if you do separation of variables without error. Yes. Oh, you're right. I put in a 1. I put in a 0 for both, didn't I? So C should be -1. Darn it. You're right. C is -1, yeah? Okay. Just before you get too far, check your derivative, your antiderivative. Did you get either by u sub or mental u sub, the antiderivative is negative log of absolute value of 1 minus y, not log of 1 minus y, right? Did you have a negative du? Okay, cool. Continue on as you were. We do need to solve, so I hope you can deal with the absolute value well. What did I do wrong? Oh, okay. Okay. So I get to a stage where y is 1 plus or minus e to the 1 minus x. What do you think? Based on the initial condition, if it is when x is 1, y is 0, which of those would hold true? Minus or negative or positive? Negative. It would have to be negative, then negative. So I'm going to go with y is 1 minus e to the 1 minus x. You follow? Yeah. All right. Say we, in the interest of 2 minutes, we wanted to check our work. Let's do y dx. 0. It should be 1 minus y. I agree. Okay. But it is, isn't it negative e to the 1 minus x times an inside derivative of -1, or e to the 1 minus x? Is that the same as 1 minus y? Well, isn't this the same as if I moved e to the 1 minus x over and subtracted 1? Okay. All right. That should do. We're not going to have time to go over the homework, but at the very least, we got that done. So tomorrow we'll go over the test, go over questions on 2 sets.
Variance statements.
Oh, not so much. I guess that's it. Have a nice day. Did last night's homework go pretty well, or we gonna need a, so we won't need a lot, but, all right. Cool.